Hello, everyone. Happy Earth Day and welcome to our webinar. This webinar is being presented by the Clean Energy States Alliance, and the topic for today's webinar is load growth and electric system reliability. We have an excellent guest speaker with us today, but before we pass it over to them, I'd like to go over a couple of webinar logistics. We are now using Zoom webinars. If you have any feedback for us, we encourage you to provide it in our post-webinar survey or via email. All attendees are in listen-only mode, so your webcam and microphone are disabled. The chat function is also disabled. You may submit questions and comments via the Q&A panel. We encourage you to submit these questions throughout the webinar. We'll be saving 15 to 20 minutes at the end of the webinar to address the audience questions. Automated captions are available, and speakers' bios will be made available in the chat. Finally, this webinar is being recorded. We will email you a webinar recording within 48 hours, and it will also be posted on CISA's website at cisa.org/webinars. And with that, I'd like to pass it over to our host for today's webinar, Executive Director Warren Leon.
Hey, thank you very much, Serene. Before we jump into the webinar, I want to give you a little bit of background and some context for why we're doing this webinar. First of all, the webinar is being hosted by the Clean Energy States Alliance. We're a national membership organization. We've been in business for more than 20 years, and our members are public agencies, mostly state energy agencies in 21 states across the country. And these member agencies work together to share best practices, identify new cutting edge technology options and program options, and work together to advance sound energy policy. If we could go to the next slide. You could see here a slide with our members' logos on there. You could see there's a good range of organizations from across the country. And if we could go to the next slide, we're doing this webinar today for two reasons. One is the topic of load growth and system reliability is a very important one. It's one that state policymakers and other stakeholders are increasingly focused on, and so we want to present information on that. But we're also using it as a lead-in to an event that we are holding in Washington, D.C. on May 28th and 29th, the National Energy Summit for States. The summit is restricted to state and federal government employees. State and federal government employees can attend for free. And on top of that, we have scholarship available for one state government employee from each state to attend. We're expecting an exceptionally good event there with more than 200 people from across the country. If you are a state or federal official and want to find out about it, check out our website at the address you see on your screen. And one of the reasons we picked today's topic as a lead-in to the summit is that the topic of load growth and what states should be doing in response to that is going to be featured prominently at the summit. If we could go to the next slide. I'd like to introduce our webinar speaker, Mark Olson. When we were looking at who we should get to talk to folks about the issue of load growth and system reliability, we naturally turned to the North American Electric Reliability Corporation, or NERC. They focus on long-term and seasonal reliability assessments, and those assessments are widely used by industry regulators and energy policymakers. Mark Olson is manager of reliability assessments at NERC, and while there, he has led several projects for developing reliability standards to reduce operating, cyber, and physical security risks to the bulk power system. Before joining NERC in 2012, he was a career officer in the U.S. Navy, and he has a master's degree in electrical engineering from the Naval Postgraduate School. So, with that as a way of introduction, let me introduce you to Mark. And I have to tell you, I have looked at their presentations and slides, and I can guarantee you that you will find it interesting and useful. Thank you.
Warren, thank you so much, and greetings to everyone on this Earth Day. It's a really privilege. It's a real privilege to be part of your lead-in to this very important summit that you're having in just 1 month's time, and I'm delighted to be able to talk with you about some of the work we've done at the North American Electric Reliability Corporation and some of the recent events that we've had that have really highlighted what I think is going to be a cornerstone of the summit as you gather and talk about energy policy, energy trends, and programs that can help ensure your missions are completed, and that a part of that is that the reliability of our electric system is maintained. That's absolutely at the center of what we do here at the North American Electric Reliability Corporation. NERC is a not-for-profit international organization. As Warren said, one of the really important things we do at NERC is to perform reliability assessments per the Energy Policy Act here in the United States, and also in Canada with agreements that we have with provincial governments. Our reliability assessments are used in informing reliability across our interconnected North American system. So I'm going to share with you some insights from our recent 2024 long-term reliability assessment, which was released in last February, and I encourage you to look at it and welcome any questions that you have about it. I'll describe some of our methods that we use in the LTRA that we publish every year, and share the key findings that we found. One of the central points that we found, and it was reiterated recently at the Reliability Leadership Summit, which I'll talk about also today, is that we have a growing need for more resources. And it's become more urgent than at any point in recent times. A big component of that is the rapid load growth that is in the industry forecasts for the 10-year horizon that we look across. So you're gonna hear that. It adds to kind of the resource adequacy trends that are shaping the challenges of maintaining sufficient electricity supplies here in North America. But before I talk about the long-term reliability assessment, I wanted to highlight the recent Reliability Leadership Summit that was held at NERC's offices was held in Washington, D.C. And I think this is also something that could be very informative to you. And fortunately, there are video recordings that are available for you to take a look at as you prepare for your own summit. I'll say the Reliability Leadership Summit really brought together the industry leaders and state and policymakers and trade association leaders to discuss what they see as the pressing reliability issues on the horizon. It is an important step every year in NERC's performance of a reliability issues evaluation that gets leads to the publication of the Reliability Risk Priorities Report reflecting what senior leaders in the industry and in the regulatory ecosystem see as the challenges lying ahead. And I'll say that it came through very clearly and was kind of a key undertone throughout this summit was that the dramatic load growth that is coinciding with our present challenges and headwinds to building infrastructure and bringing in new resources is a key concern. As you listen to these presentations and hear the discussion, I think one of the key takeaways that emerged was that solving the challenge and maintaining sufficient supplies in the future really is going to take an all-of-the-above approach to resources. The new wind and solar and battery resources that are able to speedily come onto the grid are welcome and are very much going to be important to meeting the load growth that is projected in the near term, but at the same time, preserving some of the resources that we currently have, carefully evaluating when generator retirements can occur, also needs to be the part of the equation in order to meet the future demand. There's also new and exciting technologies for demand side management that will have a role. So it's all of the above approach is going to be needed to maintain the reliability of our system. But at the same time, the concerns that these leaders shared had to do with the ability to build fast enough, given that the permitting challenges that exist, also the engineering and planning challenges of maintaining a reliable grid are part of that as well. And then potential for supply chain issues. And we currently have some supply chain issues and the future, uncertainty in supply chains can add to challenges with new resource development. So these after our webinar, the presentation slides are made available, and these links will take you to some really excellent panel sessions. And the insights from this work will help shape the focus that NERC places on addressing challenges going forward. So with that, we'll start talking about the long-term reliability assessment now. If you'll go to the next slide. This is a report that NERC publishes annually, and it's released towards the end of each year. And it is a 10-year look ahead on our energy and capacity risks and also emerging trends for reliability. The information that is used is collected directly from the planners and the operators, the owners and operators of the bulk power system in these 20 assessment areas that you see on the map here. Representatives of companies like PJM, MISO, also vertical utilities, and like Southern Company, and regional reliability entities participate on our development process and help provide the data that we use in our risk assessment. So this report can be valuable in that it is what the industry is projecting to see over that 10-year horizon. Another way that this report, I think, is valuable is the level of review and technical input that goes into it. NERC develops the report from the data that we have. It is peer reviewed by each assessment area, looking at what the other areas are working on and how they're responding to the challenges. And then it goes through extensive review with the stakeholders that participate in NERC's open processes. So the long-term assessment, again, is published every year, and it can add value because we're not really using a lot of simulation or projections with a lot of assumptions under them. It is what the system is currently planned to look like over the years. Go to the next slide, please, and I'll talk a little bit about some of the key findings from the 2024 LTRA. In our capacity and energy risk assessment, which I'll provide some details here in just a moment, we found that over half of North America is at risk of energy shortfalls over the next 10 years. And one of the drivers for that is the level of growth being seen in demand projections and the chase for resources and development to take place to meet that rising demand. At the same time as we have this escalating demand, we have the continuing retirement of aging fossil-fired plants, and retirements projections over the future years remain at pretty high levels as we've seen in past reports. And that accelerates the need for more resources to come in and replace them and keep up with that rising demand. A lot of the drivers for demand growth are familiar to you at this point as you're hearing and discussing those in your work. There is electrification of many infrastructures that is playing a role. At the same time, we have new loads being built, and some of them can go on the grid very quickly compared to historical large load development. And so that is what really challenges the load growth projection. It adds to uncertainty. Also could lead to more growth. Some of those rapid growths are about the ability to build out quickly on the load side. So that is a component to that adequacy assessment and a key trend that we're tracking every year in our assessments. I'm going to show you here in a minute how we're looking at future resources coming in, because we maintain a good line of sight on what is in the development queue. And we observed in this past assessment that the additions were falling in slower than projected in prior years, causing some concerns. But on the plus side is transmission development. There is more transmission development coming through, at least entering the planning stages. And that's a good opportunity because transmission development can help deliver the energy from where it's being generated to where it is going to be used. Next slide, please. So this is our risk map, kind of laying out the areas where we see risk. And as we noted, we see increasing energy risks over the next 5 years. And in just a minute, I'll talk about some of the drivers for those risks. But first, I want to kind of highlight how we evaluate risk and categorize the risks that we see. The colors on the map fall under the high, elevated, or normal risk categories that we've developed. A high risk indicates that it's possible in the next 10 years that shortfalls could occur in the normal peak conditions. And elevated risk are areas where they have the resources to meet normal peaks. That means they're meeting their resource adequacy criteria. But in our evaluation through probabilistic measures and other scenario analysis, we see the potential for shortfalls to occur under more extreme conditions like low resource generation, low output, low wind, for example, or higher thermal generation outage scenarios that are based on some historical events and scenarios that we put together. The areas that are in light blue are considered normal risk. They're meeting their adequacy criteria and are expected to have resources to meet supplies under a wide range of conditions. So the method we use, kind of the assessment inputs that go into making this determination are rather expansive. We don't want to look just at normal conditions to make our adequacy assessment. So we use probabilistic assessment studies that include demand and resource profiles based on historical information. And we specifically study select years in the assessment horizon, looking out at year 2 and year 4. We also evaluate planning reserve margins. These are essentially the level of excess or additional generation that is expected to be available above the projections for demand and a certain level of reliability margin built above it. And we evaluate those over the near-term assessment period. Our criteria for deciding what becomes a high, elevated, or normal risk generally follows established criteria such as the 1 day in 10 loss of load criteria, which is rather time-tested and standard resource adequacy criteria. But then we also use energy metrics that look at, for example, loss of load hours or expected unserved energy that comes out of the probabilistic assessments. And our criteria is documented in a NERC and National Academy of Engineering workshop report, if you want to look at it. But essentially, these energy criteria that we use there are really important because as our resource mix has changed, as our society's reliance on electrical energy has grown since the early days of an electric grid being formed, it's important to quantify the unserved energy that a system would have over the years, because that is really reflecting when the customer is not being served, and the impacts that can go with that are wide-ranging. If you'll click the next one more button here, I'll talk about some of the drivers as we're still on this slide here. You know, as we performed our analysis and looked at the trends over the years, we see that some of the key drivers happening to fuel these risk assessments. I hit on a couple big ones right off the bat, but demand growth is affecting multiple areas, essentially driving up those demand forecasts used in these assessment inputs, and the resources are chasing to catch up. And we're seeing some exposure there, either in our probabilistic assessments or in the reserve margin starting to dip. Add to that some generator retirements in the primarily the market areas where the generator retirements are more at risk of being unpredictable and potentially getting out in front of a planned where a planned reliable system would want to be. The risk of generator retirements exists there, and there are planning processes to prevent specific generators from retiring when they could cause a reliability problem. But when we look at resource adequacy, it's that uncertainty from out into the future of what generation is going to stay and what potentially could retire that can become a big concern to ensuring that we have enough resources planned to be able to meet our needs in those future years. Some of the areas like SPP and California, and to some extent Texas, the risk of limited dispatchable generation is a way of describing the conditions where the amount of dispatchable generation, like a gas-fired power plant or a battery resource on the system, is not at the levels to be able to meet all of the potential shortfalls that can come with variability in wind and solar and demand. In these areas that we noted as having limited dispatchable generation, we see either scenarios or probabilistic values that indicate there's shortfall periods that can occur or are occurring in some of the assessment work that we do. If you'll go to the next slide, I will talk about our what energy shortfall risks mean in the context of one area. This is the Texas ERCOT system. As I mentioned, we do probabilistic assessments, and at the top here, we're showing some of the numerical results of the probabilistic studies that we do for 2026 and 2028, alongside a comparison to the last time we ran a Prob A. So that 2026 with a star on it, that's the results from the last Prob A, so conducted in a prior year. The key thing to note here is that the expected unserved energy and loss of load hours are being calculated in these energy analysis, and those are indicating that the risk is at an elevated criteria It's met our criteria for elevated risk, meaning that they are expected to have they're expected to have enough resources to meet their normal conditions, and they're meeting their resource adequacy criteria, but there's loss of load hours emerging in the study periods that are concerning. And really mean resource adequacy decisions should consider the level of acceptable unserved energy and load loss, and balance that in the way that energy policymakers like yourselves all take into account. The bottom picture, though, is where it shows some interesting insights that we're able to understand by looking at these probabilistic assessments. And what we're showing here is 2 representative risk days from the load loss studies. The one on the left is a summer day where a load loss event is found to happen in their probabilistic analysis. And it's what you can understand from this is that it's relatively short. It's a 1 to 2 hour shortfall event. It's not the deepest shortfall. That little red area is a small, in the hundreds of megawatt shortfalls, and there are options for overcoming that that the operators would look to take into account to be able to manage that as best they can. The right side, though, shows what a loss of load event in our analysis looks like in the winter months, and you can see here that it's a much more severe and concerning event. And this is not a surprise as we've experienced tragic events like Winter Storm Uri and really overall the challenging conditions that can happen in winter. Here, the load loss event is longer, on the order of 12 hours. It is deeper, and so the solution space to how you overcome a loss of load event like that is really going to require different sets of resource adequacy tools. A short duration battery in the midst of winter will have less ability to solve challenges like this. So it's really important that those flexible resources like a gas-fired generator with reliable fuel, available fuel, and properly prepared to operate in winter, those are the kind of tools to address that. So these are some of the insights that we can show, and we're just showing one representative area and what energy risks look like as described in the long-term reliability assessment. If you'll go to the next slide, we can review our some of our analysis on generator retirements. Overall, our assessment accounts for the expected generator retirements that are likely to happen over 10 years. Our sources for this are the industry themselves, the planners reporting to us the generators that are in the planning system for retiring. And in that previous analysis, the things I've showed so far, there's 78 gigawatts total of thermal retirements over the 10-year horizon that are part of that analysis and part of those shortfalls that we found. But in addition to that, there are another 37 gigawatts of generators on the bulk power system that have announced plans to retire or are in a retirement, or early in a retirement process for this whole same 10-year period, but they have yet to enter into planning processes and therefore have not been taken out of those previous risk maps. In some areas, there's significant amounts, as you can see with MISO and PJM. So some of the market areas, there's some uncertainty about generators and potential for generators to retire earlier. So all this to say, more generator retirements would, clearly fuel the need for more resources to come onto the system to meet the demand that we have and that we expect to have, and replace the resources and energy provided by these. This is a kind of a simplified reliability insight. As generators retire, there are other considerations like the reliability benefits that a generator provides in the way of system inertia and the ability to ramp and meet the changing and variable load. And so our future resource mix is very different than the types of generators that are retiring. But we can tell from just looking at these announced retirements that we should expect to need to replace quite a bit of generation for what is currently planned to retire and what could retire and what is in considering retiring. Next slide, please. So your topic for the webinar was demand growth, and you're getting ready for a summit where you're looking at energy policy and addressing what has emerged in recent years as really a key driver to what has been a kind of mounting resource adequacy challenges as the resource mix has been transitioning. Demand growth in the 2024 LTRA was the highest in the past 20 years, and really just showing the comparison here on this right chart shows how peak summer demand has increased in our past 3 LTRAs, and really a significant step change. I'm currently working on the 2025 summer reliability assessment, and I can say that the trend is playing out as indicated in the long-term assessment. Peak demand for this upcoming summer is forecast to increase by 12 gigawatts, which is more than twice what it increased last summer. So demand growth is taking shape. So what's driving it? I don't think there's I understand that there's a lot of reporting on this. We've shown in this picture here kind of what the drivers are by different parts of our system as reported by the entities there. Data centers clearly are playing a role in many areas. We know that some of the highest growth is occurring in PJM, the Southeast here, and also Texas. But many areas have potential are seeing data center growth in their areas. Cryptocurrency development is maybe a little bit more selective in where it is. It has different attributes, and in some ways, operate now that we are having more years of experience with cryptocurrencies coming on the system. There is some evidence that their variation at peak load times is actually diminishing that impact on load. So they're scaling back operations in Texas, say during times of peak demand where the prices are going high. So it's really, I guess, all this to say it's insightful to kind of understand what the drivers are. And this depicts some of the factors. In the future LTRA, the new LTRA that we're working on, we are planning to collect more information that can help us quantify what the drivers are in each assessment area. But at this point, for the 2024 LTRA, there's some description in the report on quantifying how much load growth is happening by different types, but we'll be adding a more consistent analysis for our next LTRA. Next slide, please. So kind of along the lines with the Texas insight, that energy insight that I showed, but that effect of winter demand, winter load growth, and the winter resource adequacy challenging becoming the more important priority, or at least or possibly an equal priority to adequacy designers is occurring. We basically see winter peak demand growth outpacing summer growth. In our LTRA, the chart at the right here shows for the past 2 years now, that 10-year growth rate for the winter has outpaced the summer growth. What's driving that? Well, part of it is the electrification affecting both seasons. It can also be electrification of heating, taking more of an impact or having more of an effect on peak demand in winter. And then on the summer side, it is a number of factors, but could be efficiency in the demand, the cooling systems, also the effect that distributed energy resources and solar PV is having on reducing peak demand, and demand side management, those types of things. So most of the assessment areas that are summer peaking in our assessment, that is, they have their highest demand and their most constrained resource adequacy periods in the summer, have winter growth rates that are exceeding their summer growth rates, and several of them are able to anticipate either becoming a dual peaking system or switching over to a higher winter peak than summer peak. Most of them it's after 2030, but it is there are several areas that are seeing over the next decade or toward the later part of our 10-year horizon this shift. It's important because resource planning for winter needs to really think about things differently. The performance of generation is different in winter. Load forecasting becomes more challenging in winter, particularly as these loads are changing to more of electrified heating systems. And fuel risk is a driving concern for winter. On the next slide, please. I'm going to talk about resources, and I'm going to come back to winter here in a second. But resource coming onto the system, we continue to have very active, strong interconnection queues, a lot of resources in development to come to the system. The chart at the left shows what is in our interconnection queue in a couple of, either has a signed interconnection agreement or is nearing that phase. It is largely solar and battery that dominate the interconnection queue. The queue has grown since last year by 44 gigawatts or 12%. So that's very healthy. We need to, so the resources are there, and the system planners are developing or improving their processes to bring them onto the system. What we are seeing, though, in the data is that resources came onto the system slower than what was projected from the prior year. Project delays, cancellations, supply chain issues, all can contribute to that. But our takeaway in reviewing the data from that we collected for 2024's LTRA and comparing it to what industry was projecting to come onto the system in the prior year shows that in most resource types, the projections fell short of, the actual build outs fell short of what was projected. The one exception to this is battery resources. Battery resources came onto the system at a level higher that exceeded projections, and that's good news. Battery resources have been very valuable in summer, in just the prior year's summer, and so it's a good growth trend there. But concerned that on the whole, resources are being added slower than anticipated, and echoing that kind of concern that there are headwinds to bringing new resources onto the system that pose resource adequacy challenges. Next slide, please. Alongside the winter, the winter resource adequacy, focus looking out at the resource mix, it is natural gas is a very important generating supply for most of the North American bulk power system. And what we're showing here is all areas that have 35% or more natural gas fired generation capacity for their winter resource mix. Natural gas fired generation is important for balancing variability in wind and solar. But in wintertime, it requires increasingly, it is largely the fuel of choice that is providing energy to meet demand for winter, when oftentimes the peak demand period occurs before the sun is up. So natural gas fired generation is important, and these percentages that you see here are essentially an indication of how much of the peak demand is being met by a gas-fired resource on a peak winter day at a peak winter period. It's important that we understand the gas system, we understand the fuel availability challenges that sometimes generators face, and that generators are planning to have assurance of fuels. Much work to be done to ensure gas and electric coordination, and it's never more important than in wintertime. Next slide. So as I mentioned before, a bright spot is that we see for the first time in past several LTRAs that our transmission development trend is increasing. Over the past several LTRAs, there's been an average of about 18,000 circuit miles of transmission in a development process, either in planning or under construction. But as you can see on the chart on the right here, that is exceeded for this LTRA, upwards of 28,000 miles in development. So that's good news. Transmission is generally being developed to help connect new resources, but also to maintain the reliability of the system. That essentially means as the planners are doing their planning studies and accounting for load growth and new resources and where they're at, upgrades are needed to the transmission system to ensure that it can withstand the disturbances and reliably deliver energy supplies. We are still looking for that uptick in construction, though. The data that we collect indicates that our transmission under construction has not significantly increased yet. Siting and permitting challenges are part of the issues, and they're affecting about 1,200 miles of transmission currently. But this is a positive trend in the development stage here. On the next slide, I'll talk about our interregional transmission capability study, interregional transfer capability study, which is important for transmission because it showed that transmission development and increasing transfer capability can help reduce energy shortfalls like those that we are describing in the long-term reliability assessment. Now, the ITCS was performed to meet the Fiscal Responsibility Act, and it involved evaluating the ability for transmission development to solve energy shortfalls in the future on the future system. There's a link here for you to read it, but key takeaway is there are several places where increasing transfer capability would allow for more transfers from areas that have excess capacity into areas that are deficient under the evaluated weather years. For this study, we looked at 12 weather years that included many extreme weather events, including heat domes out in the west and freezing events in the east. And so the evaluation here is indicating that transmission development can help solve some problems, but importantly to say it does not solve all the problems, and that transmission alone will not address all the shortfalls that are found. More resources and resource development is going to be needed. Next slide, please. So I'm getting to the point where I'll wrap up here. There are a number of emerging issues also discussed in the long-term reliability assessment that are part of that, the mounting resource adequacy and energy challenges that the industry faces. As the data centers and large industrial growth is part of our demand forecast, and we've talked about that aspect of it. But also these loads behave differently on the system, and so there are some operating challenges that are coming into focus, and NERC technical committees are established and working with industry to really understand these and work with various stakeholders, including the developers of these projects, on how to prevent reliability issues from flowing back onto the system from data centers and large industrial loads. The battery and energy storage systems is certainly been a help in a number of reliability aspects. The ability to really get the most out of these assets, though, requires a good deal of visibility in how the battery unit is being operated, and what the system operator is able to see and control or be able to influence. Also an area where technical committees are working to develop best practices and guidelines that can be used by industry and other stakeholders to get the most reliability benefit out of those resources. The electric vehicles and load growth. Electrical vehicles and electric load electric vehicles are part of that electrification and load growth component, but also the behavior on a more granular level. The behavior of those battery chargers is part of the can introduce operating challenges and part of the reliability issues that need to be addressed as we bring more electric vehicles into the North American systems. And then finally, we think it's important to consider energy drought in adequacy planning. And the challenge is that there aren't a lot of models and historical data to be able to bring into help. But recent report by National Labs highlights how when low output occurs in one resource type and simultaneously is occurring in another resource type. So for example, wind and solar both having low output periods. The likelihood for this to happen in different areas, although low, should be part of the planning process and resource adequacy design, so that you have looked at these patterns, though unlikely, these patterns, and have the ability to be able to supply energy through those, because they're not built into the models that we currently have. On my last slide, I'll just kind of highlight some of the recommendations that we have. And as you're preparing for your summit, I think you can think about these that may apply. Obviously, the context here is that demand growth and the changing resource mix really requires careful attention. Resources will be needed to manage retirements and to manage growth. And as we go through this, I think it's important to carefully manage those generator deactivations. Also, I'll hit the third one here first. The siting and permitting challenges is really a very difficult one, in that it involves many jurisdictions. But really, if we're going to address growth, we need to have the ability to bring resources and bring infrastructure, energy infrastructure, fuel, transmission into the system in order to ensure reliability. And then I'll say the second one is about NERC and our assessments. We are continually looking to improve the way we're able to analyze future energy risks. We are working on processes that'll provide for new evaluations, new probabilistic assessments that can better account for wide area weather events and the ability for resources from long distance to be able to help out in areas. And that analysis is something that we currently have some limitations in the long-term assessment, and we work to address that. So with that, I'll conclude what I had prepared and look forward to questions with the time that we have remaining. So Warren.
Hey, thanks very much. That was a great overview. I just want to let folks know, because of the number of questions, we'll run an extra 5 minutes and go to 5 minutes after the hour. We had several questions that had to do with extreme weather events. And let me start with a narrow question where somebody saw on your map that the Southwest, the WEC Southwest, was not listed as a place with elevated risk. And they questioned, shouldn't the risk be elevated there given the recent wildfires in New Mexico and regular extreme hot weather events in Arizona?
Yeah, a very good, a great comment. So in the adequacy assessment performed for the LTRA, it's using historical information about demand forecasts, resource performance, and within that historical data, there are some wide area heat events, heat domes, like the 2020, 2021 heat domes that affected large areas, and the effect that they have on the demand and resources and supply and transmission are all evaluated in that interconnection-wide assessment that is done for the West. And so that type of weather event, like a wide area heat event, is part of the assessment. I think in the case of WEC Southwest, the Southwest region, it didn't quite meet the criteria to be in a higher risk category than what it was there. The wildfires and transmission issues are not easily modeled. I think as we prepare our summer reliability assessment right now, we are kind of factoring that in, because we think that summer assessment, which kind of has a different audience, it's really about being ready to address challenges for the summer and making sure the industry and stakeholders are seeing the picture of risk. We definitely do factor in the wildfire risk and the potential it can have on affecting the transmission network. So I think you have you're hitting on an appropriate risk issue. Looking at a specific area like the Southwest, there was some risk of shortfall, but not enough to meet our criteria. And things like wildfires may not have been modeled at the level of kind of specificity that you're thinking of. And we cover that in our summer reliability assessment to get the word out.
Thank you. Well, let me ask then a more general question around extreme weather events and how you model this. One listener wrote in, do you use FEMA National Risk Index data? And if not, what other data sources do you use to assess the likelihood of different weather-related and other variations that impact reliability? And do you have a sense as to, which are the top hazards affecting reliability? Is it temperature extremes, hurricanes, rainfall, something else?
Yeah, okay, good. Several things in there. I'll first say some of the nuance of our report is that we currently, as the assessment is performed, there are various entities performing the probabilistic study, and their methods can vary. We bring it all together and put together the risk assessment. So the specific profiles for demand, the types of extreme events, there can be some variation, but generally, as I mentioned with the Western analysis, for example, the heat domes of 2020 and 21 are built into their probabilistic model. In Texas, Winter Storm Uri and Elliott is also built into their probabilistic model. So there can be some variance, but I think the extreme weather events that are known and understood are part of the analysis and become part of the modeling. It is a capacity and energy risk assessment. So it is primarily looking at the things that influence the resources and the demand in the resource adequacy kind of sense. Things like hurricanes and wildfires are often not easily modeled or not part of those kind of equations that go into how that affects demand and supply. So really, I think the chief things you're seeing are kind of weather drivers like heat domes and polar vortexes that sort of dominate the modeling for extreme weather that goes in. Those are kind of the biggest ones.
Thank you. Well, look, let me ask you a broader question. I've heard a few state energy policymakers and regulators say that they think, NERC, given your focus on reliability, that you may have a tendency to overemphasize reliability concerns and push for unnecessarily large reserve margins. How would you respond to those skeptics to encourage them to view NERC's assessments as accurate and not exaggerating load growth pressures?
I think that's a really important thing to talk about here. First, I have tremendous respect for the work of the policymakers and adequacy planners and regulators have, and you have a variety of information to digest to make good decisions. It's really important to understand, I think, what each of these different types of reports are telling you. So NERC is certainly reliability focused. We have our mandate per the Federal Power Act to perform an adequacy assessment of the current and future system. And that's what we do, and that's what we're describing in our reports. I think we're kind of at this juncture where there's just so much uncertainty in forecasts for demand for a number of reasons. And new resources coming into the system are also affected by a variety of influences, from the planning processes to get them in there to supply chains and policy decisions. So we definitely have a tremendous amount of uncertainty. So when NERC publishes a report, as I said, we are publishing how the industry is forecasting their system out over the next 10 years and evaluating reliability based on that. There are many other forecasts for load growth and expected future loads. Ours is developed by what the industry is currently planning and using. So we will be reliability focused. I think we have the ability. We are a nonprofit, and we don't have a particular agenda here. We make our method very plain and explain what it is and how you can use it. But I think what is central to ours and why I think ours is valuable is the use of those projections, but also our look, and we think this is very important, to look at energy risks on the whole. It's not quite enough to look at planning reserve margins and overly optimistic performance of any generation type. And so the energy risks can emerge when natural gas fuel or generator weatherization falls short. It can also emerge when wind profiles and solar are low. Every resource has its limitation. By putting these into a probabilistic analysis and looking at all hours, we're objectively looking for the risk hours and using methods to quantify that and report that out. And I think that's really important. It's something that you can use to understand unserved energy, and that I think makes a big difference in shaping your decisions about development of new resources.
Hey, thank you. One of the listeners, actually this came up in a couple questions, asked about whether NERC accounts for grid enhancing technologies in the resource adequacy assessments, things like line rating changes, advanced conductors, other methods that could improve power flows through existing power lines.
Yeah, very good question. As these are becoming more and more important to getting every megawatt value out of the system, I think our analysis does need to carefully consider them. Currently, our capacity and energy risk assessment will consider them to the extent that the planning entities are able to quantify the deliverability of resources. How much do these enhance the deliverability of resources, and can they quantify that in their generator projections and their firm transfers evaluations that we account for. So yes, they're there, and there's the mechanism to have them in there. I think there's a lot more sophistication coming onto the scene when it comes to resource adequacy analysis within the industry and also at NERC as well. So the opportunity is definitely there to be able to understand and build these into the models as the extent that the tools can do that, and make that part of the make sure those enhancements are accounted for. So there is a capability now, but I think what we're really seeing is maturing of adequacy tools and a better ability to take advantage of grid enhancing technologies in our analysis.
Well, let me ask you one more question before I give you the last word. And this has to do with batteries and battery storage durations. The current batteries typically have a duration of 4 hours. But how far in the future do you think it will be before we need to move to longer duration storage? And is that something that's been factored into any of the reliability assessment work you've done?
Yeah, thanks. So, the batteries that are coming onto the system are having a noticeable effect, currently with summer reliability. As we prepare our summer assessment right now and look at the records from past years or the analysis, we see how ramps and these evening risk periods that used to be really concerning in the really high solar areas like California and Texas are being helped out by the ability of a battery to discharge into those periods. So these are largely 2-hour duration batteries. It's solving issues right now, typically associated with summer. I think looking ahead though, and really understanding year-round reliability, energy storage, whether it's from batteries or whatever, in order to really solve the reliability challenge that is currently being addressed by dispatchable generation over a range of times, it's going to take much longer durations. The 2-hour duration batteries will have limited ability to help in winter reliability issues, as we discussed. I can't quantify, what the duration is or when it'll happen, but I think it's an exciting time with the developments of new resources that can be dispatched. The issue is we currently have, as generators are retiring, we have this need for stored energy that is really irreplaceable by, in most places, it's gas-fired generation. But the need for that really extends through the 10-year horizon that we see, and the way that that resource is going to, the need for that type of gas-fired generation is going to be diminished. It's really going to take different technologies that we currently don't see on the system to be able to ensure energy is there all the time.
Hey, well, that's a good note to end and make folks think about some of the issues we're going to have to address going forward. This has been really helpful. Before we close, is there anything else you want to say you didn't get a chance to say, or any last message you want to give to the people on the call?
Well, I just appreciate the chance to be here, and I commend you on this Energy Summit and your preparations for doing that. I'm grateful that you were considering the NERC reports, and as you tackle this urgent issue, I think you have your plates full, and I admire the work that's being done.
Hey, thanks very much. This has been very helpful to us, and I hope everybody on the call will go and look up the NERC reliability report. It's well worth your read. And thanks very much, and we'll be back with more webinars in the future. Thank you.